So here you can see this. You probably recognize this from the picture in the schematic, or sorry, in the presentation. This is an axial design compressor. And when I turn it by hand here, you can see the pistons moving back and forth. Now, there are kind of two designs of this. You find this on a lot of older GM vehicles. The original ones had reed valves on the valve plate here, and they had, you know, discharge reed valve on this side of the plate, a suction reed valve on the inner side of the plate. And that piece of it worked pretty well. The problem is they used three big O-rings that were they didn't use locating dowels between the cases. So these are pretty prone to leak. And now, you know, that design, I don't know, wouldn't call it an upgrade exactly, but it was redesigned. I think it was a cost-saving effort. That design compressor was redesigned, and they put the reed valve, instead of using a conventional valve plate like you can see here and here, they put the reed valves on top riveted them to the top of the piston. And the big problem with that was the diameter, you know, the radius. The reed valve has been bent between the center of the piston and the outside edge. It's a very short bending distance, and so they were notorious for. This is the kind of compressor that's notorious for broken reed valves. And as I said, if your gauges are bouncing, it's a good possibility that you have a broken reed valve. Now, the other design, of course, that we talked about was the scroll compressor. So here I've got scrolls in various stages, and so you know, here's a cutaway of a scroll. If we look at it here, when I turn it by hand, you see it's got a pretty unique action inside the compressor. And so what's really going on here is, you know, you've got two scrolls, and it doesn't rotate, it oscillates, right? And so it grabs the refrigerant on the outside and it rolls it into the center. There's a discharge reed valve right here in the center. The big problem with these is they're notoriously prone to slugging, liquid locking, lubrication issues. They're a delicate design. And in fact, just to illustrate that point here is a classic example of a scroll compressor that was assembled. The system was put back together with very little, improper lubrication, not properly lubricated. So you can see, and of course you can see just by looking at it here, you get a very clear sense of the amount of junk and debris that could be generated in a system like this when the compressor fails. So that's a big problem with scroll compressors. The other one I want to point out here on this is, you will find this specific. This is what we call a variable output scroll. It's got a control valve here in the rear head of it. You may be able to see a pneumatic bellows inside that control valve. You found that a lot of like mid-2000 Ford 500s, Windstars, Saturns used Jaguar even used this compressor. A problem with it is that this control valve can fail, and it will the valve fails and the customer will complain. It works okay in the morning, but once it gets to mid-afternoon, it just, you know, the air conditioning is not cold enough, and that's usually because this control valve has failed. Now, Jaguar actually has a TSP that tells you, you know, when the vehicle comes into the shop, there's a little plate on the rear head of the compressor that holds the valve in place. You can take that plate off, pull the valve out, and there's a spring that goes in ahead. I don't have it here, but there's a spring that goes in ahead of the valve. If you take the valve out, take the spring out, put the valve back in, and then put the spring back in after it and put the plate back on, that defaults the compressor to maximum displacement or maximum output all the time. And it might affect fuel economy by a few miles, but the customer will tell you that the air condition was never as cold before. So quick scroll compressor tip there. So let's put the scrolls away. And here, just before we wrap up our conversation on the scroll, here's a classic example of liquid locking, or, you know, it's just the system way overcharged and you can't compress a liquid. And as I said, scroll compressors particularly prone to liquid locking. So, and then here's our rotary vane. They're not used much, and you still see lots of them out in the field on older Saturns especially. And this is the vane. You can see there's the vane. I've just pulled it out of the slot here. These rotary vane compressors are particularly sensitive to oil viscosity. If you use too much oil, if the wrong viscosity of oil, the vanes can get stuck, and it can be really hard to get them to pump properly. So again, rotary vane compressor, turn at 2,000 RPM, oftentimes you'll be able to free up the vanes if they're stuck. Now, so let's get into, you know, the most, to what I would call modern technology. So I would say about 70% of new vehicles today are using what we call an electronically controlled variable displacement compressor. Now on the bench here in front of me, I've actually got this is old technology, probably 30 years old. This is a GM V5 design compressor, and it is a variable displacement compressor. Now, if you look here, this is what we call the wobble plate, or in more modern designs, this would be called the swash plate. It's called the swash plate. You can see how you can see how I can change the angle of the swash plate there like that. Well, inside this compressor, we're using a wobble plate, just same thing, just a different, it's got little connecting rods instead of a flat plate. And you can see the angle of that swash wobble plate has a pretty sharp angle. So if I rotate the compressor now, do you see, just watching here, there's the piston. Do you see the pistons are going back? Just watch them again. I'll get a good turn on it. You can see the pistons are going back and forth quite a distance. Well, if you look here, right here, there's a hinge. There's a hinge right there. This is the corresponding hinge on this design here. You can see hinge right there. So if I position that hinge like that, and now I change the angle, see how I've changed the angle of the wobble plate at right angles of the crankshaft. Now if I turn this compressor, do you see, watch the pistons there, they barely turn, they hardly move at all, right? And of course, if I, might put it somewhere in the middle, then I'd have a medium stroke. And so the whole idea here is, if I can, by controlling the angle of the wobble plate or the swash plate on a more modern design, if I can control the angle of that swash plate, I can literally control the pumping. I can seamlessly, smoothly, gradually change the pumping displacement of the compressor on the fly, just to match the heat load on the system. The whole idea is I don't want to take, the first advantage is, by using variable displacement, I don't have to keep constantly click-clacking the compressor clutch on and off, especially on these smaller engine vehicles that you see so many of today. The compressor is a significant load on the engine. If you have the clutch clicking on and off, it has a dramatic, pretty significant impact on the idle. The customer can feel that inside the vehicle. They may even hear it. And it can load down, can load down the idle. And also, if you've ever had a tailpipe, an emissions analyzer up the tailpipe, when the compressor clicks on and off, you see a big spike in emissions right when the compressor comes on. So the way this works is this. If you look in the rear head here, there is a control valve. If you look maybe closely, you can see an actual bellows. There's a pneumatic bellows in the rear head. And that is, this is a control valve from this exact compressor. And if we look closely at the valve, you will see there are three areas. There's 4 O-rings, O-ring here, O-ring here, O-ring here, and an O-ring here. And there's a section here, there's a section here, and a separate section here. This area here is exposed to high side pressure. The area in the center is exposed, is open to the crankcase of the compressor, the area behind the pistons and back of the pistons here. And this area here, in fact, if you could look very closely inside there, you may be able to see a pneumatic bellows. It's a bellows, and it's attached to a rod. So if the suction pressure changes, if the suction pressure increases, it's going to compress the bellows and it's going to retract the rod. And so as the rod moves back and forth, depending on whether we increase the pressure on the bellows or decrease the pressure on the bellows, we can bleed more or less pressure into the crankcase, into the area behind the pistons. And so if I change the pressure drop across the pistons, between the top and the bottom of the piston, in that way, I can change the angle of that swash plate. And so remember, suction side pressure, low side pressure is a function of heat load. If I turn the blower up on high speed, I put more heat load on the evaporator, and that's going to cause that's going to reduce the pressure on the crankcase, and that will increase the stroke of the piston. So that's how a conventional old school variable displacement compressor works. Well, along comes the latest technology that, what you're seeing in most vehicles today that use a variable displacement compressor is what we call an electronically controlled variable displacement compressor. In other words, a computer controlled variable displacement. And believe it or not, inside, the only difference, mechanically inside, the new compressors are identical to the old wobble plate style that we're seeing here. Just instead of a wobble plate, as I said, they used what we call a swash plate. And so the fundamental difference is that we imagine that I took out this pneumatic valve. And this pneumatic valve, the displacement control valve, can really only see or monitor one input, and that, as we mentioned, is suction side pressure. Imagine I took out that valve and I put it on the side, and I substituted a computer-controlled solenoid. And in fact, if we look at it closely, I've got it cut away here so you can see inside of it. There's a rod inside, just like almost like an injector in a way. And it has the same, it's got the high side area, it's got the crankcase area, and it's got the low side, just like before. One part of it's connected, is exposed to high side pressure. The center section is exposed to crankcase pressure behind the pistons. And the top area, the fatter area here, is exposed to suction side pressure. But of course, the computer can look at many, many or more inputs than just our pneumatic bellows over here. It can look at coolant temperature, high side pressure, low side pressure, ambient temperature, duct air temperature. We did some research there several years ago. I think the computer takes up to 24 PIDs into account in calculating the duty cycle command to the solenoid. So the way this works, of course, is the computer, just like an injector, if you like, by increasing or decreasing the duty cycle command to the solenoid, it can change the angle of the swash plate to make the compressor pump more or less. So that's the new technology, if you like. I'd say about 70% of new vehicles now are using an electronically controlled variable displacement compressor. So I'm going to put this one back on the back here, and we're going to take out a couple of actual electronically controlled variable displacement compressors. So here, as you can see in the picture here, this is electronically controlled compressor 1, and you can see in the back here is the solenoid, right? This is the solenoid that gets a command from the computer. Could come from the PCM, might come from a separate HVAC control module, depending on the application. And so the computer is going to send a duty cycle command to this solenoid to change the pumping displacement of the compressor, as we described before. Now, so that's one there. Let me grab another one from back here. And again, this is just from another similar. Inside, these have a swash plate. Change the angle of the swash plate to change the stroke with the pistons. So, it's a technology, a concept that's been around for a long, long time. But a key difference to notice here is that if you look, when I turn this compressor, do you see when I turn the pulley of the compressor, do you see that the clutch, the crankshaft can even, the crankshaft is turning while I'm turning the pulley. And if we look behind here, look in the back here, there is no clutch. So this is what we call a clutchless compressor. And even when it's 40 below in Alaska, this compressor, the crankshaft of this compressor is still turning. Now, of course, if it is 40 below, if I don't need air conditioning, if it's below freezing, the crankshaft will still be turning. And believe it or not, the pistons, by design, to get the pumping process started in a variable displacement compressor, you need a tiny amount of piston movement to get the initial pumping process started. So all these variable displacement compressors, even when they're defaulted to minimum displacement, they're always pumping a little bit, right? So if it's 40 below, if it's very cold out, I don't need air conditioning, the computer simply won't send a command to the solenoid here. And in fact, if you unplug the electrical connector from the solenoid, that will default if you were looking at your gauges and the compressor was working. If you unplug that solenoid on any of these compressors, the compressor is going to default to minimum displacement, and it's going to go down. The two pressures there might be a 5 or 10 psi difference between high and low side pressure, but basically the pressures will default to same pressure throughout the system. So all the early ones back in the mid 2000s, when these compressors started coming out first, all the early Asian and European systems that use this compressor, they were all clutchless, right? So just keep that in mind. However, a lot of manufacturers, because they had lubrication problems in cold weather and so on and so forth, not all, but a lot of the manufacturers today, you can see it's still an electronically controlled variable displacement, but it's got you can see the wires here. We've got a conventional clutch. So a lot of the manufacturers now are going back to using a conventional clutch on these. Still electronically controlled variable displacement, but it has a conventional clutch. Now, I want to caution you here, a couple of things. Number one, we have a tech line here at our training center. We get a lot of calls about these types of compressors where the shop has replaced the compressor several times, and but it doesn't appear to be working. In other words, the high side pressure is way low and the low side pressure is way high. In fact, most often the two pressures are almost equal, right? Well, the thing to understand is, and so think about the old, our normal, in the past, our diagnostic process would have probably gone something like this. The car comes in, the air conditioning is not working. I put a set of manifold gauges on there, and the first thing I notice is that the high side pressure is way low, the low side pressure is way high, maybe a few psi difference between the two, but basically the two pressures are almost equal. Well, traditionally that would indicate that the AC is not on, or that the compressor is no good. So if I open the hood and I look down, I can see that the pulley is turning, and I look at the outside here, it looks like the clutch is engaged, right? These are often front-wheel drive vehicles. It's going to be hard to get a total, really full-on look at it. And so to the naked eye, it looks like the clutch is engaged and the compressor is working. So if I see high pressure low, low pressure high, clutch engaged, natural diagnosis in the past would be this compressor is no good. The problem, of course, is we need to check. We need to determine, is the computer sending a command to this solenoid before we condemn the compressor itself. In other words, if the computer thinks the engine is overheating, or the clutch is the transmission is slipping, or the battery voltage is low, there are many reasons why the computer might not be sending a command to this solenoid. And if it's not getting a command, the compressor won't pump. So it's just important to understand that. Oh, and one other caution before I move on. If you do work on a vehicle, for example, I've seen the circumstance I usually see is the vehicle was at a body shop. The car got in a minor accident. The customer continued to drive the vehicle. The body shop did the grill and whatever work to repair the front end. And then the first warm day of spring, when the customer turns on the air conditioning, the AC doesn't work. And that's because if you run this compressor, even just run it around the block with even though there's oil inside, you need refrigerant in the system to keep the oil stirred up, to keep the oil agitated, and to keep all the moving parts lubricated. You never want to run this compressor with no refrigerant in the system. Otherwise, I've seen many of them seized and damaged very easily because the compressor was run. Once you start the engine, shaft is turning. If you run it without refrigerant, you're potentially going to ruin the compressor inside. So just FYI. So let's take a look at some of the basic inputs that the computer's looking at. As you recall, we talked about the high side pressure transducer. And this is typically, a lot of later model vehicles will actually have a low side pressure transducer, but most often for many years now, most systems have had a high side pressure transducer, 3 terminals inside, 5-volt reference, ground signal. You're probably familiar with that. These can be notoriously prone to leaking. They're often the source of an undetected leak. They can leak where they screw onto the line. They can leak where there's an O-ring in here where the aluminum is rolled over on it, joining the plastic to the metal. And the real sneaker is I have seen a leak where the terminals come through the plastic. Sometimes if you disconnect the connector and look inside, you might see kind of an oil stain in here. You can get a leak through the terminals as well. So, and the other issue I see with these pressure transducers is, if the transducer has failed outright, you plug in a scan tool, you're going to see the pressures 500 psi or 0 psi. It's going to be pretty apparent that there's a problem with pressure. The more sneaky failure is where the transducer is shifted. It's the calibration is shifted 10, 15, 20 pounds, either too high or too low, and that can affect the operation of the compressor and the operation and cutting in threshold for cooling fans. It's very important that this pressure transducer be accurate. Cut to the, one way to check that would be if the vehicle has been parked for some period of time and pressures have stabilized throughout the system. If you plug in a scan tool and it's, let's say, 85 psi on the scan tool static pressure, and then you connect up your manifold gauge set to the system, it should be within, 85 psi, give or take a few pounds, would be a good, down and dirty check of the accuracy of the pressure. Doesn't tell you that it's not going out of whack at a higher pressure, but a basic check would be to compare scan tool pressure with the manifold gauge set pressure. So that is my high set pressure transducer. Probably the most fundamental input to the computer especially for controlling the ECV solenoid, the displacement of the compressor, is the evaporator temperature sensor. These, usually sometimes will be just strapped to the side of the evaporator so the air passes over them. Sometimes will be probed, stuck into the fins between the plates of the evaporator. But this is my evaporator temperature sensor. And of course, if you plug in a scan tool, you'll usually see a value for evaporator core temperature, or you'll also often see a value for target temperature versus actual temperature. And again, the whole idea here is we want the evaporator as cold as possible. The computer is going to use this input to control the pumping displacement of the compressor to get the evaporator core temperature down as close to 32 as possible. But we want it down probably in the 35 to 40 degree range. But we don't want it colder than 32 degrees. If the evaporator gets colder than 32 degrees, especially in high humid circumstances, all the moisture hitting the evaporator fins will freeze over and the evaporator will be ice cold, but there'll be no airflow through it, and so you'll have no cold air coming out the duct. So that's my evaporator temperature sensor. A quick check for these, if you can, is if you get a, it's not always, some of them you can unplug them readily, easily from the dash. Extract them from the evaporator case. Some of them you have to take out the whole case. But if you can get to it and take it out and just stick it in a plug in your scan tool and look at the temperature on your scan tool. If you just put a cup of ice water, a mix of ice and water, and stick this into it, then your scan tool should read 32 degrees just about. So that'd be a quick, again, calibration check of your evaporator temperature sensor. So that's that. The other control here, I'm going to take another compressor back here that you can get a look at. Now I've taken the clutch off the front. It has a conventional clutch, this compressor, but I've taken it off so we can see what's going on. And this is what we call a 19C compressor. And you can see it's got the, it looks pretty conventional here, but it's got the variable displacement control solenoid. And it's got a conventional clutch. We've taken it off, but it all does have a conventional clutch. The other big secret here, the other kind of thing that you may not have noticed before, is this compressor has an RPM sensor. Think of a cam sensor or a crank sensor. It is literally usually a VRS, a variable reluctance type sensor, and it's reporting compressor RPM, compressor speed back to the computer. And most Toyotas, for example, will describe it, will call it out on the diagram as the belt lock sensor. And as the name suggests, the computer can see engine RPM, it sees compressor RPM, it knows what the ratio should be between the two rotating pieces. And so if the compressor starts to slip, it will detect that immediately by comparing engine RPM with compressor RPM, and then it would disengage the clutch to avoid further damage to the compressor or the belt, and so on and so forth. So this is called the belt lock sensor. Works just like a camera or crank sensor. You can scope it out if you have any doubt about it. The real new technology here that you may not have seen before is if you look on the discharge port of this compressor, a couple of things. You see here there's a sensor. It's got a snap ring holding it to the discharge manifold here. This here is what we call a refrigerant volume flow sensor. And again, it's a Hall effect type sensor. It's got a 5-volt reference, a ground, and a signal, just like many 3-wire type sensors. And if we look, I've actually got one manifold taken off here. Here's one. The sensor, it's just held on with a snap ring. The sensor does not contact the refrigerant itself, right? Inside, I can't see it here. They're inside of here, but just below the sensor. As I said, it's a Hall effect type sensor. Just below the sensor, there's a tiny little magnet balanced between two springs. And so as the refrigerant is forced out of the evaporator, out of the compressor, there is a shunt passage here. There's a calibrated restriction in the compressor output port, in the discharge port. And so the little magnet is displaced in proportion to the pressure drop across the restriction. That's how this volume flow sensor works. Just an FYI, as volume increases, voltage usually drops, and vice versa. When volume decreases, the voltage goes up. So this is a refrigerant volume flow sensor. And again, today, it's all about efficiency. The computer can tell compressor RPM, knows temperatures, pressures. Now it knows exactly how much refrigerant is passing through the compressor. And so again, now by using all that information, it can very precisely control the pumping displacement of the compressor to, reduce emissions, maximize fuel economy, and so on. By the way, just an FYI here as well, on this solenoid, I'm sure you've seen in many vehicles today, there will be some kind of an econ button in the dash. When you hit that econ button in the dash, that prioritizes fuel economy over cabin comfort. So when you hit the econ button in the dash, the computer is going to modify the command profile to this solenoid and prioritize, fuel economy over cabin temperature. So the customer needs to understand that. We often see customers complain, my air conditioning is not as cold as it used to be. And that is often because if you engage that econ or economy button, the computer is backing off on the command to the solenoid, and the air conditioning is not as cold as it could be. Or often the complaint would be it doesn't get as cold nearly as quickly as it used to. So that's another good So that's a quick review here. I will mention one other things. I see this is, if you look at this is a swash plate for one of these electronically controlled variable displacement compressors. Do you see that it's double hinged here, right here, like this? Well, here's one from a cheap compressor, from an inexpensive compressor. You see, if you could feel it in my hand, you may even be able to see it in the picture. It's got a very jumpy movement, and that's because it doesn't have a double hinges. It's just got a sliding slot to control it. These are notorious for binding and sticking, and you get erratic operation. It doesn't get all the way to full displacement, and so on and so forth. And the solenoids also, these solenoids, you can get internal leaks. And the command, the electrical piece of it may be working well, but you get internal leaks, so it's not bleeding the pressure in and out of the crankcase the way it should, or it gets stuck at a fixed position and doesn't control the displacement very well. So that's some additional tips when looking at these compressors. Here is a conventional orifice tube. I'm sure you've changed plenty of those, but I do want to kind of, if you've ever cut the end of one of these here, I've cut this one, I've cut the end off here, I've cut the end off here. In orifice tube, there's no moving parts, there's no valves, it is simply a tiny tube. It's just a tiny brass tube. It is simply a restriction to refrigerant flow. That's so I get the pressure differences that I need to make air conditioning work. Now, you will notice that it looks like it's got two filters on it. In fact, this is the filter. And so, and oftentimes this is the only filter in an orifice tube system. You can imagine it would be doesn't have a lot of real estate here. It can be very easily get clogged. This obviously is going to point back towards the condenser, or the refrigerant is coming in from the condenser here. And again, very easily clogged. This piece on the other side that looks like a filter is actually a diffuser. And it just acts as it breaks up the liquid refrigerant. It breaks up the liquid refrigerant as it enters the evaporator. So you get better, you get better boiling and evaporation. The refrigerant boils more easily if I break up the liquid flow as it enters the evaporator. The other thing to point out, of course, is that thermal by SE, by industry standards, orifice tubes are color coded. You've got red and green and white and orange here, and that determines the diameter. How much refrigerant they will flow. The color of the orifice tube dictates the diameter, the tonnage, or the capacity of the orifice tube. So that's my orifice tube system. I've actually got the cutaway that you can see in that picture. And here's how a TXV valve works. This piece here, which will unscrew from any valve, this here we call the power element, right? And it's got a stainless steel diaphragm. Think of the top of a bean can that separates the top from the bottom of the valve. In fact, I've got an older one cut apart here. You might be able to see if you look here. This is an old school valve, but the power valve is the same inside. There's a thin metal diaphragm separating the top of the valve from the underneath. And so the way this works is this. So you see there's a rod here that runs all the way from the power element, rod down through the valve from the outlet, the suction side, all the way to the inlet where the liquid comes in. And do you see if I push on this rod, it's pushing down on a ball valve. You see there's a ball bearing right there? So it's pushing that ball valve. So if I'm going to have liquid refrigerant coming in here, if I push that ball valve off its seat, I'm going to get more liquid refrigerant into the evaporator. Now, you notice that the ball valve is spring-loaded closed. This is the superheat spring here. And I do want to caution you, you do not want to mess with this. Can be removed. That's just for assembly purposes. You do not want to mess with the superheat screw here, or you'll never. This is all set up in a kind of a factory, in a laboratory environment at the factory. You do not want to mess with this in the field. So the way this works is this. So you can see that I can increase or decrease the refrigerant flow into the evaporator by opening or closing that ball valve. Well, the power element, when this power element is manufactured, it's got a small amount of refrigerant gas trapped above the diaphragm. And so, so if liquid refrigerant comes in the evaporator, it boils, changes state, and starts coming out the top. In a TXV system, I'm going to allow a small amount of superheating. In other words, I'm going to allow all the liquid to change state from a liquid to a gas so that it's pure gas coming out the top. So if I turn the blower from low speed to high speed, the gas coming out the top is going to get a little bit warmer. The gas coming out of the evaporator is going to get a little bit warmer. So if I warm that brass ferrule, that brass rod there, that brass rod is in thermal contact with the bottom of the power valve, right? So think about it. If I warm or cool that brass rod, it's attached at the bottom of that metal diaphragm. That's going to heat or cool the refrigerant that's trapped above the diaphragm. So if I heat the refrigerant trapped above the diaphragm, it will expand and deform the center of the diaphragm, which will drive the rod down, which will drive the brass rod down. And so open the ball bearing, open the ball valve wider, right? So you can see that if I increase the temperature here, the refrigerant will expand, drive the rod down. In other words, I can increase the refrigerant flow into the evaporator to match the increasing heat load, and of course, vice versa if I turn the blower back to low speed. Now, a couple of things here. I want to point out that a lot of TXV valves look the same. They can be very similar to look at, but They are all TXV valves are like a medical instrument. They're very precisely engineered and designed. They are a very exact match for the system that they're being installed on. And each TXV valve has 3 specifications. A valve will have, they can look identical, but a valve will have a specification for tonnage. In other words, how much refrigerant it will actually allow to flow. In other words, how much real estate it can cool, right? It will also have a specification for superheat. Most of them, start maybe around 4 degrees all the way up to 14 degrees, or give or take, for most automotive applications. And that superheat value is how much temperature increase it will allow across the evaporator to prevent liquid locking or slugging the compressor. And the third specification is MOP, or maximum operating pressure. That's the pressure acting in the evaporator, the pressure acting in the bottom of that diaphragm. It's the maximum pressure at which the TXV valve will allow refrigerant to flow. So it's very important that that you use, when you're replacing the TXV valve, it's very important that you use a quality valve that exactly the specifications exactly match the system that's being installed on. Don't just think that because it looks the same that it's going to work. I'm going to show you 2 condensers. If you're replacing the condenser on the vehicle, I've got 2 condensers here. And this one here it's not the original condenser, but it's similar to the design of the original condenser. This is from the mid-2000s Ford F-150. And this is what we call a Piccolo tube and fin. You can see there are tubes here going back and forth across the condenser. The point I want to make is this. This is a tube and fin, basic tube and fin design. And we have done an experiment here at our training center where we pulled a vacuum on this condenser and we charge it with liquid refrigerant. And believe it or not, this condenser will hold about 47 ounces of liquid refrigerant. Well, I'm only showing you 2 here tonight, but I've actually got 4 at the training center. And here's one of them. Here is another potential. This is a replacement condenser for this Ford F-150. I've actually still got the fittings on it here that we use to pull the vacuum on it and charge it with liquid refrigerant. This condenser here, it fits perfectly on the truck. You can have it in and out in 10 minutes if you want. Pretty straightforward. The difference is that this is a flat tube multipath flow condenser. And in our experiment, we found that the original condenser held 47 ounces of liquid refrigerant. This replacement condenser only holds 26 ounces of liquid refrigerant. And I have 2 other condensers. One is at, I think, 34 ounces, and the other one is at 42 ounces. So there's a lot of variation out there. The point I'm making is the factory charge on this Ford is 33 ounces. And if I take out the condenser I showed you first and install this condenser, this is a very flat tube multipath flow. It's a very efficient design. It's an excellent condenser. But because the internal volume of this condenser is so much less than the original, I will not be able to get this condenser to work on the vehicle without, I will need to use a technique we call differential temperature testing. We will need to adjust the refrigerant charge amount, probably reduce it from 33 ounces to get this condenser to work on the vehicle. So this is a fairly extreme example when you go from tube and fin to flat tube multipass, but just understand that oftentimes you've got to be on the watch out for that. If the replacement condenser, I'm not saying not to use it. In fact, the replacement condenser may be more efficient than the one you're taking out, but you may need to adjust the charge level to optimize the performance of the system with some replacement condensers, just FYI. So we'll put this away here for a moment. And I'm just going to show you one other thing while I'm here. Maybe not. I thought I had an actual cutaway of a condenser tube. Well, I will show you this. It's very close to approximate. This is actually a cutaway of an evaporator. And believe it or not, modern evaporators they're the exact same design as the condenser. And you can see looking in here is this is a flat tube multipass flow condenser. And when you look inside, you can see the little holes and the little passages here. the point I want to drive home here, it is impossible to flush a modern condenser. Even if the compressor hasn't failed, even if you're just replacing the compressor because it has a leak, you still need to flush the condenser to get all the contamination out of the system. It is literally, I've done the math for, I think, a Toyota application. If you add the length of all these tubes end to end, it stretches 3/4 of a mile. And so these tubes are so small, the friction is so, the resistance to flow is so great, it's just impossible. Once you try to put flush solvent or anything of that nature in here, plus they're often dammed at several points along the header tank, it's impossible to flush a flat tube multi-pass condenser, just FYI. So the accumulator performs 4 functions. It acts as a storage device, so there's a little bit of excess refrigerant to compensate for different heat loads in the system, so it's kind of a storage tank if you want to think about it like that. It's also got the desiccant medium. So if we cut this open, it's full of beads inside, and it's a desiccant medium. It's XH7, XH9. It absorbs trace moisture from the system to prevent corrosion and acid buildup and so on and so forth. And I've seen them missing. We've cut cheap ones apart over the years. I often see them missing or some rogue flower or something inside of them. So that's storage, desiccant medium to absorb trace moisture. But its most fundamental function of the accumulator is it is a liquid vapor separator. So remember, the refrigerant coming in from the evaporator is going to come in here. And remember I said on an accumulator system, it's going to be 95% gas with a little bit of liquid, right? So of course the liquid is going to drop down the bottom of the can. And don't forget that liquid refrigerant is carrying the oil. It will be carrying the oil that's circulating in the system. It'll carry that oil up and out of the evaporator and into the accumulator, and the liquid with the oil will drop to the bottom of the can. The gas, of course, goes to the top of the can. The refrigerant gas goes to the top of the can. And this piece here we call the J tube. This piece here we call the J tube, and you can think of it as a snorkel. It reaches almost at the top, not quite, but almost at the top of the can, and this end of it is connected back to the compressor. This is the suction line going back to the compressor. So the compressor is drawing refrigerant gas from the top of the can down this J tube and back out to the compressor. Now, as the gas is drawn down the J tube, it creates a Venturi effect, a low pressure area in the J tube. And what happens? Do you see there's a little barrel filter here right at the bottom of the J tube? If we look carefully here, you may be able to see it. There's a tiny pinhole in the very bottom of that J tube. And so remember, and this is very important, this can will be 1/3 to maybe 1/2 full of liquid refrigerant and oil. So as the gas is drawn down the J tube, it creates a low pressure area, Venturi effect, creates a low pressure area just above the pinhole. And through that pinhole, we get a fog of oil and refrigerant, micro droplets of refrigerant being drawn through that pinhole and mixed with the gaseous refrigerant being drawn back to the compressor. And that fog of oil, micro droplets of oil and micro droplets of refrigerant being drawn back to the compressor, keep the compressor lubricated. And the micro droplets, when they hit the hot compressor crankcase, they evaporate, and you actually get, latent heat of evaporation. You actually get a cooling effect. So the pinhole provides both lubrication and cooling for the compressor. And if you undercharge a system 10, 15%, you will get ice cold air. And that's because every molecule of the refrigerant gets to evaporate inside the evaporator. But if there is no liquid covering the bottom of that J tube, you will have the compressor will seize. It'll go out the shop blowing ice cold air, but it'll come back to you in days or weeks or months, depending on how low it is, with the seized compressor because it's not getting any lubrication. So that's the function of the accumulator. And a receiver dryer. And so the function of the accumulator ensures that liquid vapor separated to ensure that no liquid arrives at the compressor. The receiver dryer fulfills many of the same functions. Remember, it's found on the high pressure side of the system in the liquid line. It's got the desiccant medium. We've cut this one apart here. It's got the desiccant medium inside. The receiver dryer also has a fairly big filter inside to prevent debris getting to the TXV valve. You can see a long pickup tube that's supposed to go all the way to the bottom, almost at the very bottom of the can. And that's the liquid vapor separator function. So it's like an aerosol. It picks up liquid from the bottom of the can. And the receiver dryer, so it acts as a liquid vapor separator, but in reverse to the accumulator, meaning that it ensures that only pure liquid arrives at the TXV valve. And that's important, believe it or not. If you run a TXV system low on charge, if you've turned the faucet on in your house, I'm sure with air still in the system, you've worked in the plumbing, I'm sure you've seen those bow, 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 like rapid, violent explosions of air out of the faucet when you turn it on. Well, if you get air bubbles, gas bubbles going up in the liquid line here, when they hit the TXV valve, the violent pressure pulsations, maybe 150, 200 psi in the system, the violent pressure pulsations can actually damage. It'll bounce the rod off the ball valve off its seat. It can actually damage the diaphragm of the TXV valve. So that's the function of both your accumulator and evaporator. About flushing tools. So a lot of shops I go into, I try to get out in the field as often as I can. I walk into a lot of shops, and this is the flush tool that they're using. And this, has a port on here where I can use an air chuck. So I put a quart of solvent in here. I charge it with maybe 50, 60 pounds of static air pressure. And then I hold this rubber tip, this blower tip, up to the evaporator outlet and, hit the button and try to flush the evaporator. I often say a bad flush is worse than no flush at all. Meaning, if I use a tool like this here, the air is going to expand, drive some of the solvent out, then it runs out of oomph. The pressure drops rapidly, and what ends up happening is all the solvent drops out inside the evaporator. And now you've got a dirty soup of abrasive metal particulates and dirty oil in the bottom of the evaporator, 2, 3, 4, 5 ounces. And now if you put the system back together, when you charge it up, that dirty soup gets pushed out of the evaporator, and it takes, it tears the compressor apart in record time. A much better tool is what we're looking at here. Do you see it's got an air chuck, so I can connect up shop air to it. It's got a pressure gauge, so I can actually control the pressure through the evaporator. And I can actually, it's got the valve on it, so I can actually, so I can control the air pressure. It's also got a shut-off valve, so it's got an actual, so I can dial the pressure up to, let's say, I'll dial the pressure up to 40 psi, and then I might give it a squirt like that very quickly to soak the evaporator for a little bit, and then I turn this valve, the shut-off valve, back on, and I allow the continuing air pressure maintains the solvent momentum through the evaporator to prevent any kind of solvent dropout. And then when all the liquid is expelled, which only takes a few seconds, I actually dial the pressure up to 80 psi, and I walk away. And I can walk away because this tool also has a universal adapter. You see this universal coupler here? I can use that. So you can see I've cut it just for demonstration purposes here. I can use that. I can attach this universal adapter to a line or to the evaporator, and I can, it's a permanent attachment. I don't have to stand there holding it, so I can, do the flush and then dial the pressure up to 80 psi, walk away, and let the shop air, especially if you use dry shop air, it does a powerful job of drying out, drying up any residue in the bottom of the evaporator. Just FYI, so in other words, here is an evaporator that I have here. And note that I've got, so here's an evaporator. You can see here's the TXV valve, and here's the suction line and the liquid line. And there's an old liquid and suction line that I took off of a vehicle. Oftentimes you will find that while the TXV valves are very unique to the vehicle, the basic block, 4 or 5 blocks might fit 80% of the vehicles that you work on. So what I do is I take an old piece of liquid and suction line like you can see here, right? And then I take the TXV, you can't flush through a TXV valve, right? But I attach my flush tool here, like this, the tool that I just showed you. I can attach it here like this, and so I can flush, reverse flow. I can flush through the evaporator and back out to the TXV. But as I said, you can't flush through a TXV. But what you can do is, like I have here, I'll just put this evaporator over here. What you can do, if you notice, I can, like I showed you before, I can unscrew the power valve, right? So I unscrew the power valve, you take out the metering rod, you can take out the superheat spring here, and the ball, the ball valve that we showed you before, then take a 1/2-inch drill bit. I think you can see here how I've drilled it out. I take a 1/2-inch drill bit and I drill it out. And now I've got a perfect, very cheap, inexpensive flush adapter. I reattach it to the evaporator. I use the old suction liquid line that I just showed you, attach my flush tool, and now I've got a very inexpensive but powerful flush adapter for my flush tool. A question that comes up a lot is, whether to replace hoses or flush them. So a couple of quick things. First of all, hoses are, rubber hoses are, the base compound is rubber. It's organic. It came out of the side of a tree. It's been heat cycled. The truck is, 8, 9, 10 years old. The rubber's been heat cycled 10,000 times. So oftentimes, the rubber, here's a crimp joint here. It's been crimped for the past 10 years. It's been heat cycled 10,000 times. The rubber hardens, shrinks, crystallizes. And so the micro leak that led to the low charge oil dropout compressor seizure is often, very often, in fact, I would say it's the primary cause of original compressor failures is micro leaks from hose crimps. And so honestly, when you count the cost of flush, the cost of your time to do the flush, and the fact that you're flushing a 10-year-old hose, and if the compressor came in with a hole in the side like this here, when are you going to be able to pressure test this system? When you've done the entire repair, evacuated and recharge it, and then right at the end of all of that, you find you have a leak. Often it is literally cheaper to replace the hoses at the outset than to be trying to leak check a 10-year-old hose that you don't even know, or trying to flush a 10-year-old hose that you don't even know if it's leaking yet or not. Another quick point about hoses is often you look under the hood, it'll have some kind of a bubble or a can like this here. If we look inside, look at this muffler here. The line goes in here, it goes all the way hard up against the end of the can. And the only way for refrigerant to get through here is there's 4 pinholes around in the tube inside. If you get debris inside that can, forget about flushing it. You're never getting it out of there. Here's one here, this bubble here, looks like it's just a bubble in the line, but inside of it is a paper filter. And again, this was an actual case study we had here years ago. If the lines have a bubble or some kind of a thing that looks like any of these in the hose, in the line, and the compressor has failed, I highly recommend that you replace the hose assembly rather than trying to flush it.